Hi everybody, welcome to another video in Discrete Math section 4.2 Integer Representations and Algorithms. Right. So, integer representation. So the normal way we do is the base 10 or the decimal. 965, we have 965. The one on the right is the base 10 to 0 power, and then next to first, then the second, and forward. So we go from right to left, pretty much. So that's the base 10. So this section we study the base 2, the binary, the 8 octal, and 16 hexadecimal. So that the way the usually computers use that. Of course, there are other bases as well. Could be 4. Of course, pretty much any number. The Mayans use base 20, and the Babylonians use 60. If it's 60, that means they have to be 60 different digits. That's very difficult to compute. I suppose when I have 20, so maybe use all the digits and all the fingers and toes, probably. Anyway, so base B representation. So let's just like what we have. The last one times b to 0 power, and then going forward up to the k. Alright, it's called the base B digit representation. Right, so we write that as this coefficient. If it is base 10, we don't really need to write base 10 because that's just a decimal system, normal system. Right, let's see how this look. First we have the base 10, base 2. That's called the binary. In this expansion, the only digits used are 0 and 1. So as we see later that whatever the base is, we're going to use from 0 to that number minus 1. So that would be like 2 to be 0 and 1. The base 8 will be 0, 1, 2, 3, 4, 5, 6, 7. The 8 of them, right? Now, the one on the right doesn't have any power. This times 2 to the first, times 2 to the second. So we have 0, 1, 2, 3, 4, 5, 6, 7, and 8. Count from 0. So in this case, we write this as 1 times 2 to the 8 plus 0 times 2 to the 7 plus 1 times 2 to the 6, 0 times 2 to the 5th, 1 times 2 to the 4th, 2 cubed, 2 square, 2 to the first, and then 2 to 0 power, or just 1. Right, 2 to the 8 is 256. That's 0 to 664, 32, 16, plus 8, plus 4, plus 2, plus 1. So all of that. So 256, 64, 16, 8, 4, 2, and 1, 351. Right. Next we have this. So 0, 1, 2, 3, 4. So 1 times 2 to the 4, 1 times 2 cubed, 0 times 2 square, 1 times 2 first, and 1 times 2 to 0. So 16, 8, 0, 2, and then 1. So that 26, 27. Right. So that is the binary. Next we have the auto system, which is base 8. If base 8, we go from 0 to 7 because they're 8 of them, right? 8 digits. Base 8. Right, so again 0, 1, 2, 3, the first 7 times 8 cube, 0 times 8 square, 1 times 8 to the first, and 6 times 8 to the 0. Right, a cube 512, I think. Yep. So 7 times 512. Of course, if we write a number like this, that's base 10. That's 0, 8, 6. 7 times 5, 112, plus 8 plus 6, 35. Later on, we'll just ignore the last one. That may be confusing. The last one doesn't have any power. Right, 598. Now 111, 0, 1, 2. The last one has no power. So that is 64 plus 8. 64 plus 8, 72, 73. Right, just like that. So that is base 8. Now next base 16. Well, base 8 is okay, but base 16, the problem with that is we need we need base 16, so we need 16 different digits. We have 0 to 9, that's only 10. So in that case, we go capital letter A stand for 10. B is 11. C 12. D 13. E 14, and F is 16. Find the decimal expansion for this. Right, so we're just going to use 2. Okay, 0, 1, 2, 3 times 16 cube plus E is 14. Last one is 15, sorry. Base 16, so it's not going to be equal to 16. 14 times 16 square plus 0 times 16 to the first plus 5. The last one, they just drop the power. Right, now we just need to do this. 16 cube. Just do everything at once. Plus 14 times 16 square plus 5. That's what we have. 11,781. Next, C for 16. C is 12 times 16 to the first plus 4. 196. So it's very easy to convert any base to base 10 to decimal system. Now if we have to go back from one base to another, how would we do that? But mostly, at least we can go from any base to base 10. Now if we can go base 10 to any other base, that would be good. So the base 10 is kind of the intermediate step. We go everything to base 10 and from base 10 to everything else. Right. So the algorithm is given like this. Actually, this. So in this case, we say that the base B expansion, first we're going to divide, and then after divide, we take the remainder, and then just keep writing every remainder backward. Right. So we start with first, if this into base 8. So base 8 we have to divide by 8. So we start with 8 go to that. Right here, so we can use a calculator. 1, 2, 3, 4, 5 divided by 8. Of course, give you that. In that case, just take the whole number times 8, and so that is 1 less than the dividend. So we have to actually write out if we divide here, the quotient is 1543. Actually, this one we should write it backward. Sorry, I forgot. Okay, that's fine. Let's just write 8 of 1543, and remainder is 1. Alright, now dividing, take 8, that divided by 8, 1543 right. Now 1543 divided by 8, I will just do that, 192. Now we take 192 times 8. Right, so that missing 7, which is 192. So we divide, take the quotient, take remainder, take the quotient. 192, remainder 7. Then we take A go to 192. It's 24. Remainder 0. Now divide 8 by 24. Remainders again is 0. And then we take 8 1 to 3 and 0, remainder 3. So we stop where we have 0 here. So the key here is we're going to write that in reverse. So this will be equal to 30071 in base 8. Right. Now actually let's write this out. When we do this, we can just say it. Actually, there's a better way to do this. Just divide it backward, even better. Of course, you can also say it 1, 2, 3, 4, 5 equal to, we're going to take that and then with that we can rewrite 1543 is 192 times 8 plus 7, and then we just keep doing that. 192 is 8 times 24, or 24 times 8. And then times 8 again, plus 7 times 8. And then 24 is 3 times 8, 8 plus 7 times, I forgot 8. 24, 3, 8, that 8, that 8, 8. And I multiply that 3 to the 8 to the 4th plus, oh, sorry, forgot the remainder of 1 on the outside. So that equal to 7. Sorry. That equal to 3. There's 0, 0 here. There's a 7. There's 1. Right, so that's how we write that. Another way to do this is even better, is dividing backwards. So we start from the bottom up. 1, 2, 3, 4, 5 divided by 8. What do you get? When we divide this, we have 1, 5, 4, 3, remainder is 1. Next, divide by 8. 192. This is much better when you divide backward like this. Remainder 7. Divide by 8. 24 evenly. Divide by 8. 3. Remainder 0. And then 8 to 3, 0 time, remainder 3. And again, just 3, 0, 0, 7, 1. That is, if we divide from the top, bottom, from the top, we just take the order in the right order. If we divide from top to bottom, we have to reverse the order. But either way, we have the same thing. Now this is the funny thing. 24 base 10 is equal to 31 base 8. So this, like say, Christmas Eve, wait, that's 24, 25. Okay, I need to verify that. It could be 25, I might forgot. But 31 octal base 8. So 31 base 8 is equal to 3 times 8 to the first plus 1 times 8 to 0. Actually, it is 25. So Christmas is the same as Halloween. Kind of that same. Right, 25 by 10 is 2 times 10 plus 5, which is also 25. Both of them. Right, so just like that. Well, the reason that we particularly want to go to base 2 by 8 and 16 is this. If you see that I went from 0 to 16, and we said each octal digit corresponds to a block of 3 binary digits. Each hexadecimal corresponds to a block of 4. So with this, the conversion will be easier. And so we keep this conversion. Okay. Now try we convert this string of numbers. Right. So let's convert this to base 8. 1 1 1 1 1 0 1 0 1 1 1 1 0 0 base 2. Now we convert to base 8. Now we group 3 1 2 3, and now we just add the 0 in front of it. 4. So we have 0 1 1, where 0 1 1. Oh, that's 3. 1 1 1 7. 0 1 0 2. 1 1 1 7, and 1 0 0 at 4. Right, base 8. Yeah, so base 8 we just group the group of 3. If we need to add 0 in front of that, do it. Right, now we convert to base 16. I'm going to add, we need the block of 4 for hexadecimal. 4 4 4, and also need 4 if we need to, like, do extra 0. But of course we just look for 11 in the hexadecimal. Where's that? Okay, anyway, binary 0 11, that 3 in hexadecimal, that also 3. Now 1 1 1 1 0, that here, which is 14 in decimal, but E in hexadecimal. 1011, 1011, that B, and 1100 C, 16. Yeah, so it's convenient to do that, to convert between the octal, hexadecimal, and 2, pretty much, because 2, 16, and 8, all of them base of 2. Of course, you can select base 4 as well, but that might be useful too. But start right. Now we have the operation on the binary. Of course, this is strictly for the calculator, because the calculator process the bit of 0 and 1, so they do a lot of multiplication and addition. Right. So, of course, if we add, if it is even, if we add two numbers, convert to decimal. If it is even, it's going to be, of course, we can always convert to decimal and then do the math, but here we say we're going to do this operation. Right, so I'm just going to leave that there for add and multiply using the binary. Now more to that is, if we want to convert something to the power fast, this is a way. For example, if we have 3 to 11, up there we could just take 3 times 3 times 3 times 3 times 3. That's too much, right? Think about this. First, we convert 11 into base 2. 1 times 8. I've just used the greedy algorithm here. So from 2 11 to construct, we have the most base 2, so that will be 8. Do we have any 4s? That will be 0. And there's a 2. And then 1. There's no base. Right, so that is 2 cubed, 2, and 1. So keep that in mind. The 3, the first, and the 1. Right, so what is 3 to 11? We can say is that 3 to the 8, 3 to the first, times times 2. Right, so 8 plus 2 plus 1, 11. Right, all of them are base of 2. Now, we know 3 square is 9. Now 3 to 8, we can say 3 square, which is 2 square, that will be 4, and square again, that's 8. Times 3 square times 3 to the first. So this will be 3 square is 9, square, square. I'll keep doing that, sorry. 9 square is 81. (81) square. So 61 times 9 times 3. So this is a faster way than just take 3 times 3 times 3, 11 times. Right. So 177,147. Right. That's nice. Next, the algorithm for computing the product of two n bits integers. So I'm just going to leave that here for completion of the section. Right, with that, I stop section 4.2 here. As always, thank you for watching and see you in another video in Discrete Math.